Hey audience! Last time I managed to get a decently high frequency out of my signal generator, but with lots of phase noise caused by inconsistent delays in the code. Samples would usually be sent out with very few instructions executed between them, but occasionally there would be a long delay as the code processed the input from the ADC. One thing that we can take note of is that within this main loop there are two things that we have to do: output samples and handle user input. Outputting samples must be done as fast as possible and with strict timing to prevent phase noise, but handling user input can be done at a much more leisurely pace. Even as infrequently as 5 times a second, then the user will never notice a difference. I'm going to call these chunks of code loop kernels, for lack of a better word. I don't know if it's common to refer to the thing that a loop does as a kernel, but I think the word kind of fits. To give you an idea of the concept that I'm going for here, the word kernel can refer to small chunks of code that things like graphics cards run lots of copies of, or to a small window into some data, like an image, that gets processed for every possible position within the data. So why not just refer to it as a loop body? Well, they're not quite the same thing. In this simple case, the loop body is also the loop kernel, but in something like a partially unrolled loop, the loop body contains multiple copies of the kernel. And in our case, we can, if we want to, divide the loop body into 2 different kernels based on their timing requirements. I'm going to call these the Tortoise and the Hare kernels to sort of generalize the idea, but also because I think it's kind of a cute name for them. So my idea here is to make the loop body contain 1 copy of the Tortoise kernel, and then split up the Tortoise kernel at regular intervals and insert a copy of the Hare kernel. This way, the Tortoise kernel can have as much code as it wants and run as slowly as it wants, and the Hare kernel will still be guaranteed to run periodically, and with very strict timing if we're careful about counting clock cycles. There are a few things we'll have to be careful of when doing this. One is that the Tortoise and the Hare kernels need to use different registers so that they don't interfere with each other. This is pretty easy in this case, since the Hare kernel needs 1 temporary register, which we can change to something that the Tortoise kernel never uses, and it's also the only thing using the X register. We also need to be careful that the Tortoise kernel sets both halves of the step size variable in 1 block, but we use a single instruction to do that, so that's easy. A less obvious thing to worry about is the status register, SREG, which contains flags related to arithmetic operations, like carry and overflow. The Hare kernel adds things, and the add instructions clobber all of these flags. So we need to save SREG before the Hare kernel and restore SREG afterwards if the Tortoise kernel code uses or checks any of the flags. This is necessary in the scaling code, where we do multiplication and division with multi-byte values. And boy howdy did this one give me some problems. It took me an embarrassingly long time to realize that I had to save and restore the SREG. It showed up as phase noise, so I assumed it was my cycle counting that was wrong. I managed to narrow it down to the multiplication code by commenting out different parts and seeing when the phase noise went away. Eventually I had all the code uncommented except for the parts that copied the result of the scaling code into the registers for the step size variable. For some reason I still thought it was timing related until I noticed the frequency would jump in discrete steps when I turned the knob small amounts. I remember having the same issue earlier when I had messed up my multiplication code. It happens when the upper byte of a multi-byte value doesn't change when the lower byte rolls over. So once we make sure that the 2 kernels don't step on each other's state, we also need to be careful to count the number of clock cycles that each instruction takes in the Tortoise kernel. The longest instructions I might expect to run would take 3 clock cycles, so I decided to split the Tortoise kernel into 3 clock cycle chunks. With a 5 cycle Hare kernel, this turned into a nice even 8 clock cycles between samples. Sometimes instructions will just take 2 or 3 clock cycles, and then we end up not being able to get exactly the number of clock cycles we want in one of these blocks. In these cases, we can insert a no-op instruction as clock cycle padding, since they only take 1 clock cycle, and then we can take the 2 or 3 clock cycle instruction and just push it downwards into the next block. This will make the Tortoise kernel run a little bit slower, but who cares? It's the Tortoise kernel. I also found it useful to make sure that each sort of paragraph of code was a multiple of 3 clock cycles. So I wouldn't have to worry about changing one section and then having to clean up nearby sections to make sure the timing fit. Again, this makes the code a bit longer than it needs to be, but it really doesn't matter. Another thing is that conditional instructions will often take a different number of clock cycles depending on whether the condition is true or false. We can see that with these skip if instructions, for instance, where it takes a single cycle if the condition is false, and it doesn't skip the next instruction. and it takes 2 or even 3 clock cycles if it does skip the next instruction, depending on what the next instruction is. This ended up not causing too many problems, I just had to be a bit careful. So this ended up working really well. I have a very clean signal of no phase noise, and what's more, I can actually make precise statements about exactly what the frequency is for any given step size. I know that there are exactly 8 clock cycles between samples, and at the clock frequency of 16 megahertz, that leaves me with 2 megasamples per second, which I'm kind of proud of. With my maximum step size of 2560, that puts me right at 78.125 kilohertz. I can obviously tune my maximum step size to change that maximum frequency, but I think that's pretty respectable. But if I ever wanted to change the way that the user interface behaves, like add new buttons or knobs or whatever, that could get difficult. I can put basically whatever code I want in the Tortoise kernel, but it takes quite a bit of time and effort to get it split up correctly. But I have a plan to fix that too, and it's a little bit ridiculous, and I'm very excited about it. But that's for the next video. I'll see you then.